My name is Rudy Venter, and today I will be presenting my final year electrical engineering project, the Tesla Coil High Voltage Resonant Transformer. My supervisor for this project was Mr. J.C. Packer. The presentation structure will consist of the following sections indicated below. Nikola Tesla was born on July 10, 1856 in Croatia. At 26, he conceived ideas for AC generation and rotating magnetic field theory. Some of his influential patents include that of the induction motor, the transformer, and radio control. At 35, he conceived the Tesla coil with his vision for wireless power transfer. The Tesla coil has historic applications in the spark gap radio and X-ray devices, and modern day applications which include use within particle accelerators and generating high voltage displays. Motivation existed to design, simulate, and construct a piece of equipment for Stellenbosch University's Electrical and Electronic Engineering Department's high voltage laboratory that could reliably generate high voltage, high frequency, low current discharges for the following educational and following research purposes. The solution proposed was to develop and simulate and construct a rotary spark gap Tesla coil in conjunction with safety control and monitoring. The objectives for the rotary spark gap Tesla coil system are listed below, including the objectives for the discharges and power consumption. Safety control and monitoring system objectives include those for safe user operation, user control, and user system state monitoring. The Tesla coil operates on a two-phase cycle. During the first operational phase, indicated in green and denoted by 1, the 50 Hz AC mains voltage gets stepped up via the high voltage transformer. During this step, the spark gap is deionized and the resultant 50 Hz AC high voltage charges the primary capacitor C1 with a voltage equal to the sinusoidal voltage at the current instance in time. A negligible voltage drop occurs across the primary inductor L1 due to the voltage division being in favor of the capacitor due to its much greater impedance at the lower frequency. When the capacitor C1 reaches full charge near the positive or negative peak of the 50 Hz sinusoid, the potential across the spark gap is at its greatest and is enough to ionize the spark gap, resulting in the second operational phase. During the second operational phase, the ionized spark gap results in a short circuit and thus isolates the circuit loop indicated in red from the circuit loop indicated in blue. In the red loop, the secondary of the high voltage transformer is short-circuited and thus has no connection to the blue loop. The blue loop forms a primary LC circuit with a great primary capacitance from a capacitor bank and a small inductance from a low-turn primary coil. The LC loop formed by the secondary circuit consists of a high inductance coil and a low capacitance toroid capacitor. The fully charged capacitor discharges and the current and voltage starts to oscillate at the resonant frequency of the LC circuit combination, governed by the following equation. The oscillating current in the primary coil, L1, generates a magnetic field which in turn weakly couples magnetically with a secondary coil L2, which is in close proximity. The energy stored in the primary capacitor is then transferred to the secondary circuit with an identical resonant frequency combination governed by the same equation. For optimal transfer, the transfer energy accumulates in the secondary top load capacitor C2 until the potential difference between the top load capacitor and the surrounding environment is great enough for dielectric breakdown and ionization of the surrounding air to occur, discharging the stored energy into the surrounding environment in the form of a high voltage arc at the resonant frequency. When all the energy is transferred from the primary capacitor to the secondary circuit, minus real losses occurring in the spark gap, the potential across the capacitor, and thus the spark gap, is at a minimum, resulting in deionization and quenching. The capacitor is then charged again according to the high voltage supply AC waveform, and the cycle repeats. Next, we will be looking at the design of the complete Tesla coil system indicated in the low-level diagram, consisting of the safety, monitoring, and control section, the high voltage supply, the primary circuit, and the secondary circuit, with its accompanying external variable inputs. First, the AC high voltage supply had to be designed, and the decision was made to use a center tap topology. The short circuit and open circuit tests were conducted to characterize the high voltage supply in the form of microwave transformers. They were then simulated using LT-Spice and an oscilloscope with a high voltage probe to yield the following optimal high voltage outputs for the stationary spark gap and rotary spark gap operation. During phase 2 of the Tesla coil operation, the secondary is short-circuited, thus increasing primary current. The decision had been made to implement a series primary inductor to limit the current to the transformer, indicated in the LT-Spice diagram here. The simulations had been run on LT-Spice and physical tests had been implemented along with calculations yielding the following results for optimal operation. To prevent damage to devices connected in parallel to the AC supply of the high voltage transformer, the decision had been made to implement a low-pass filter The low-pass filter would filter out the high-frequency noise, as indicated by the following results. The decision was made to implement a variac to be able to adjust the output voltage of the high-voltage supply. The spark gap consists of a two-spark system, the safety gap and the rotary gap. The safety gap ensures safe system operation in case a fault occurs, and the rotary gap fires utilizing rotary electrodes spinning between two stationary gaps. Here, the ANSYS Maxwell simulation shows that the rotary gap will fire reliably and the stationary gap won't fire under normal operating conditions, which is optimal. This graph indicates a uniform field between the gaps, as indicated by the test results. The design capacitance for the primary capacitors was 45 nanofarads. The implemented capacitance was 45.66 nanofarad, indicating proper construction. The primary capacitors also have a 500 megaohm resistor in parallel to ensure safe discharge within 135 seconds. In the case a fault occurs, a user does not get hurt. The primary inductor was implemented using an Archimedes spiral, indicated here by the ANSYS Maxwell simulation. The simulation, test, and design results are concluded here in the following table, and including lead resistance for the tests and the ANSYS Maxwell simulation, the primary inductance was matched to ensure optimal resonance of the primary circuit. The decision had been made to implement the secondary coil utilizing a helical inductor, resulting in the following calculation, simulated, and test inductances. In the secondary coil, an interesting amplified occurrence of the skin effect also occurs, as indicated here by the simulation and tests. The decision had also been made to implement the secondary capacitor utilizing a toroidal top load. This toroidal top load was simulated in ANSYS Maxwell, indicating high E fields on the wires of the constructed toroid, which will show where the discharges will protrude from. Tests, simulations, and calculations were also conducted on the change of capacitance versus the distance from a ground plane. Capacitance in the secondary also occur between the windings as well as accumulated in the top load. The resonance test was then conducted to calculate the winding capacitance. The resonance test had also been conducted on the complete secondary circuit to calculate the complete secondary capacitance resulting from the toroidal top load and the interwinding capacitance. As can be seen from the table, the calculated and tested resonant frequency of the secondary coils are close to one another, indicating proper design and construction. In a Tesla coil, a low coupling coefficient is desired. The coupling coefficient could not be calculated manually, and ANSYS Maxwell was utilized to calculate the coupling coefficient. The short-circuit open-circuit test for coupling was also conducted to calculate the actual tested coupling coefficient and mutual inductance. The calculation, ANSYS Maxwell, and test results yield similar values, indicating proper design and construction. To ensure resonance matching of the primary circuit and the secondary circuit, the primary coil had been tapped in the correct position to ensure the correct inductance for resonance matching between the primary and the secondary, resulting in the following calculation and test results, which are close to one another. To implement safety control and monitoring, the following design schematic had been constructed. The sum of all design results in the following complex system diagram originating from the simple system diagram. The following is the 3D implementation of the complete Tesla coil system. The following is the physical implementation of the safety control and monitoring system with front user interface, the internal component, and the DC to DC converter for the rotary spark gap speed control. The following is the physical implementation of the complete Tesla coil system. In conclusion, all the Tesla coil system and safety control and monitoring system objectives were achieved. Future recommendations for the system include improving the rotary spar gap rigidity, being able to adjust the secondary coil height above the primary coil, and finally implementing Bluetooth wireless control. This concludes the presentation. The following is a brief presentation on the Tesla Coil High Voltage Resonant Transformer poster. First, a bit of background history on Nikola Tesla and the Tesla Coil for some perspective. The project motivation includes the main motivation of constructing a piece of equipment for Stellenbosch University's high voltage laboratory that can generate high voltage, high frequency, low current discharges. The proposed solution being the construction of the rotary spar gap Tesla coil, with some objectives for the arc length created by the Tesla coil and the power consumption. Also, objectives for the safety control and monitoring system that will be implemented. Then, a brief introduction on how a Tesla coil works, and the complete Tesla coil system with a function of the individual components. Also, some fields on the secondary capacitor, the primary and secondary inductor, and the rotary spar gaps are shown. Then, the function of all the individual components of the safety control and monitoring system are shown here. Also, a low-level system diagram for easy digestion of the system, and a high-level system diagram for the more experienced reader. The Tesla coil output is shown here, with air discharges, ground discharges, strike rail discharges, and wireless power transfer. In conclusion, the project was a success in the construction of the rotary spar gap Tesla coil and the accompanying safety control and monitoring system. Future improvements include improving the rotary spar gap, the movement of the secondary coil for better coupling, and upgrading the control circuitry to allow Bluetooth control. Thank you. I look forward to your questions in the presentation questioning session up next.